Yellowstone's caldera has been subsiding at a pace of about 2 to 3 centimeters, about 1 inch, every year since 2015. However, the deformation varies seasonally as a result of changes in the amount of water present both above and below ground. Although the surface of the Earth may appear to be steady, it is continually moving. Due to tidal influences, a large portion of this motion is regular. Subsidence caused by groundwater withdrawal or uplift brought on by tectonic processes are both possible in specific areas. Ground motion can be particularly dramatic near volcanoes, and the ups and downs reveal information about what is occurring below the surface. Extreme deformation can occur at some volcanoes. For instance, Campi Flegrei in Italy experiences many feet of uplift over brief periods of time. There are examples from that region, the Galápagos, and other coastal volcanic locations of deformation occurring so swiftly that fish were trapped as formerly submerged areas rose above sea level. At Yellowstone, deformation is not as significant. There is some movement of the ground, however it usually only moves a few centimeters, 1 to 2 inches, annually. Measurements of the caldera's level taken between 1923 and 1977 showed that it rose by 72 centimeters, 28 inches, but that this rise was followed by a period of subsidence in the 1980s and a return to uplift in the 1990s. It is evident from geologic studies of terraces on the north side of Yellowstone Lake that, over the past 14,000 years, since the end of the last ice age, the caldera has generally sank by around 30 meters, 100 feet. INSAR, a satellite technology, and continuous monitoring of global positioning system, GPS, stations have both been used to track deformation at Yellowstone over the past 20 years. Unlike INSAR, which cannot be utilized in the winter because snow obstructs the satellite signal, GPS gives data year-round, regardless of the season. The Yellowstone caldera has been subsiding by around 2 to 3 millimeters, about 1 inch, each year since 2015, according to GPS data. At stations on the east side, close to the mud volcano area, and on the west side, next to Old Faithful, the subsidence may be seen. This subsidence is happening throughout the caldera. The subsidence is not constant, though. Every summer, it is broken up by a pause or even a negligible rise of between 0.5 and 1 centimeter. Beginning in May or June and lasting until September or October, the subsidence stop and slight uplift occur about at the same time every year, though some years it is more noticeable than others. This seasonal signal is being caused by what? When you plot the deformation data against the river levels, the answer becomes obvious. As river levels start to rise as a result of runoff from spring snowmelt, the seasonal pause in subsidence starts to occur. With this runoff, the groundwater system is refilled, which causes the ground to swell like a wet sponge. This runoff also makes the rivers run higher and faster. The seasonal deformation in Yellowstone is not solely due to groundwater. In the vicinity of Yellowstone Lake's edges, signals are also visible. The spring lake level increases quickly as a result of much runoff, while the summer lake level gradually falls. A 1.5 meter, 5 foot, change in lake level is possible. Similar to placing a bowling ball on a mattress, all that more water places more weight on the ground's surface, causing it to sink. GPS devices close to the lake may see the weight of all this water. A subsidence of up to 2 centimeters, less than an inch, can be seen at GPS stations close to the lakeshore throughout the spring when the lake level rises. The bowling ball is gradually lifted off the mattress as the lake level drops, reversing the subsidence. Even while they are typically not as spectacular, if you consider a few centimeters significant. Areas outside the caldera see some of these seasonal variations as well. Still, the caldera is where most of the current subsidence is occurring. In recent years, there have been episodes of uplift and subsidence in the area surrounding the Norris Geyser Basin, which deforms independently of the caldera and suggests that water is building up beneath the basin and then being released. Yellowstone National Park's ground motion is dynamic, varying from year to year and even from season to season. Caldera subsidence has dominated since 2016, But at some point, it will begin to rise once more, as it did most recently between 2004 and 2009 and 2014 and 2015. One of the biggest magmatic and hydrothermal systems on Earth goes through ups and downs, and this is a part of it. Meanwhile, here's everything you need to know about the Yellowstone caldera. The Yellowstone caldera, commonly referred to as the Yellowstone supervolcano, is a massive volcanic depression that is situated in the western central region of Yellowstone National Park in northwestern Wyoming. It is about 50 kilometers by 70 kilometers, 30 miles by 45 miles in size. The term caldera, which derives from the Spanish word for cauldron, refers to the deep crater that makes up a significant chunk of Yellowstone National Park. The youngest of the three biggest calderas in the park, the Yellowstone caldera is more than 640,000 years old. The area was influenced by extensive glaciation, considerable mountain formation, and extensive volcanic activity during the Cenozoic era, 66 million years ago. As a result, the Absaroka Range was created on the north and east edges of the present-day park. Intense volcanism that resulted in widespread volcanic eruptions started around 16.5 million years ago, close to the borders of modern-day Nevada, Oregon, and Idaho. Over 100 calderas were formed over a 500-mile route as the North American plate shifted southwest over a shallow source of magma. Due to the partial emptying of magma chambers after significant eruptions, calderas typically form following the collapse of the top of a volcanic cone or group of cones. In the years since, the Yellowstone region has experienced 3 more large eruptions, 2 of which released more than 240 cubic miles of magma, ejecting a magnitude of 8, the highest possible rating on the Volcanic Explosivity Index. The Mesa Falls eruption took place about 800,000 years ago, while the Huckleberry Ridge Tuff eruption was the region's first significant eruption, occurring around 2.1 million years ago. The Yellowstone caldera was created 640,000 years ago as a result of the eruption at Lava Creek. During these eruptions, a tremendous amount of hot volcanic rocks were dispersed outside. Thick sheets of hard rock were created as a result of the accumulation and adhesion of hot ash, pumice, and other rock pieces. Most of the continental USA was blanketed with volcanic debris from these eruptions, and some of it was found as far away as Louisiana. The Sour Creek Dome and the Mallard Lake Dome, 2 resurgent domes within the Yellowstone caldera, may only be 3 to 8 miles above magma. As magma volume and hydrothermal fluids move between them, both domes have the ability to expand and contract. The caldera floor has tilted to the south over the past century as a result of net inflation, forcing trees on Yellowstone Lake's southern sides to stand in water, and a sandy beach to form at the lake's northern end. Rhyolitic lava flows that erupted 70,000 years ago were the result of Yellowstone's most recent volcanic eruption. The Pitchstone Plateau, located in the southwest of Yellowstone National Park, was created as a result of the greatest floods. With between 1,500 and 2,500 earthquakes detected each year, the Yellowstone region is very seismically active. Even though the majority of these earthquakes have magnitudes that are too low for humans to feel, seismological monitoring technology can nevertheless pick them up. A large landslide in Madison Canyon and rock falls in Yellowstone were caused by the 7.3 magnitude Hebgen Lake earthquake in 1959, which also claimed the lives of 28 people. These events also blocked roads and severely damaged buildings in West Yellowstone. Since 1973, the Yellowstone region has seen more than 48,000 earthquakes, yet almost 99% of them were just 2 or lower in magnitude, and no one was affected. In addition to the one earthquake with a magnitude of 6.0, 1975 also saw 2 earthquakes with a magnitude of 5, 29 with a magnitude of 4, and 379 with a magnitude of 3. Nearly half of the seismic activity in Yellowstone is caused by earthquake swarms, which are earthquakes that cluster in both time and location. A few swarms can contain thousands of earthquakes and linger for months, but the majority are modest and only contain 10 to 20 earthquakes, lasting only a few days. The greatest of the 78 earthquakes recorded in June 2023 by the University of Utah seismograph stations in the Yellowstone National Park region was a moderate 2.8 magnitude earthquake that struck on June 17 at 11:58 a.m., roughly 17 miles to the north-northeast of Mo Run, Wyoming. As Susan Meissner says, it is the nature of the earth to shift. It is the nature of fragile things to break. It is the nature of fire to burn. You can suggest topics you want to see next in the comment section below. Please subscribe to Weather Collapse if you want to know more and be updated on the latest news about natural calamities or disasters happening all over the world, and don't forget to like today's video. We'll see you in the next video. Thanks for watching.